Have you ever looked up at the night sky and wondered if everything we know about the universe is actually wrong? We think of space and time as the fundamental stage on which the cosmic drama unfolds. But what if that stage itself is warped, twisted, and behaving in ways we can't explain? Today, we diving deep into one of the most perplexing mysteries in modern cosmology, the CMB cold spot. Back in 2004, a satellite named WMAP was mapping the oldest light in the universe, the cosmic microwave background, or CMB. This is essentially the afterglow of the Big Bang, a faint radiation filling all of space. It's remarkably uniform, but not perfectly. There are tiny temperature fluctuations, hot spots, and cold spots that represent the seeds of all the galaxies and structures we see today. But WMAP found something unexpected. In the direction of the constellation Eridanus, there was a patch of sky that was abnormally large and unusually cold. So cold, in fact, that the odds of it appearing by chance in our standard model of cosmology were staggeringly low, something like 1 in thousands. It was nicknamed the CMB cold spot. Now, a slightly colder patch of sky might not sound like a universe-shattering discovery. But in cosmology, a field built on statistical probabilities and precise measurements, an anomaly like this is a giant red flag. It's a clue that screams, you might be missing something big. The initial reaction from the scientific community was a mix of excitement and skepticism. Could it be a glitch in the satellite's instruments? A mistake in the data analysis? Then, in 2013, the European Space Agency's Planck satellite, with much higher precision and different instruments, looked at the same patch of sky. The result? The cold spot was still there. It was real. This ruled out an instrument error and confirmed that we were looking at a genuine feature of our universe. The mystery only deepened. Our best model of the universe, the Lambda CDM model, which beautifully explains so much from the expansion of the universe to the formation of galaxies, simply couldn't account for a cold spot this massive and this cold. The probability was just too low. It was like flipping a coin and having it land on its edge a dozen times in a row. You'd start to suspect the coin is rigged. So, if it's not a random fluctuation, what is it? One of the first and most plausible explanations proposed was the existence of a supervoid. Imagine the universe as a giant cosmic web with long filaments of galaxies and dark matter surrounding vast, empty regions called voids. A supervoid would be an exceptionally large and empty one of these regions. The idea is that as photons of the CMB light travel through this supervoid, they lose energy. Why? It's a phenomenon called the integrated Sachs-Wolf effect. Light climbing out of a gravitational well loses a bit of energy, making it appear colder. In an expanding universe, a supervoid's gravitational pull weakens over the time it takes for light to cross it. So, the light doesn't get the same energy kick on its way out as it lost on its way in. The net effect is a slight cooling. This seemed like a perfect solution. A giant, empty bubble in space, sitting right between us and the cold spot, could explain the temperature drop. Astronomers immediately got to work, pointing their telescopes at that region of the sky to map out the distribution of galaxies. If there was a supervoid, there should be a noticeable lack of galaxies there. Several surveys were conducted, and they did find a void. It was even nicknamed the Eridanus supervoid. The problem was, it wasn't super enough. While there is indeed a large, underdense region of space in that direction, it is not nearly empty enough or large enough to account for the full temperature drop of the cold spot. It could only explain a small fraction of the observed coldness. The supervoid was a piece of the puzzle, but not the whole picture. This is where things get really wild. With the most normal explanation falling short, physicists started to consider more exotic and, frankly, more mind-bending possibilities. One of the most fascinating ideas is that the CMB cold spot is not a what, but a where. What if it's the signature of another universe bumping into our own? This comes from string theory and the idea of the multiverse, where our universe is just one bubble or brane floating in a higher dimensional space alongside countless others. According to this theory, if another bubble universe collided with ours in the distant past, it would leave a bruise on our cosmic microwave background, a circular, cold signature. The CMB cold spot fits that description almost perfectly. This is a truly profound idea. If true, the cold spot would be the first ever observational evidence of a multiverse, confirming that we are part of a much larger cosmic reality. It would transform our understanding of existence itself. It sounds like science fiction, but it's a testable hypothesis. A cosmic collision would not only create a cold spot, but should also subtly distort the polarization of the light within it in a very specific, non-random pattern. So far, analysis of the Planck data hasn't found this smoking gun texture, but the search continues. The data is incredibly complex, and finding such a faint signal is a monumental task. Another theory, just as strange, suggests that the cold spot could be a defect in the fabric of space-time itself. Think of what happens when water freezes into ice. Sometimes imperfections, like cracks or crystal dislocations, can form. Some physicists propose that as our universe cooled after the Big Bang, similar defects, called textures, could have formed in the fabric of space-time. A collapsing texture in the early universe could, in theory, create a large cold spot in the CMB with the exact properties we observe. Like the multiverse idea, this would be a direct window into the fundamental physics of the universe's first moments. And the theories don't stop there. Some have proposed that the anomaly could be caused by the gravitational pull of a structure outside the observable universe, a hint that our cosmos is far larger than the part we can see. Others wonder if it's a sign that our understanding of gravity on cosmic scales is incomplete. Maybe gravity behaves differently in these vast, empty regions than it does within galaxies. Each possibility forces us to confront the limits of our knowledge. So what is the CMB cold spot? Is it just a 1 in 1,000 statistical fluke that our standard model allows for, but just barely? Is it the shadow of a giant cosmic void? Is it a bruise from a collision with another universe? Or is it a scar in the very fabric of space-time? We don't know. And that's what makes it one of the most exciting mysteries in all of science. It's a genuine anomaly, a crack in our otherwise successful picture of the cosmos. These are the kinds of cracks that future breakthroughs are made from. Every great leap forward in physics, from Newton to Einstein to quantum mechanics, began with an observation that just didn't fit. The CMB cold spot is today's anomaly, pushing us to ask deeper questions and imagine a universe that is far stranger and more wonderful than we ever conceived. The answer is still out there, waiting to be discovered in the faint, ancient light from the dawn of time. Thank you so much for joining me on this journey to the edge of cosmic understanding. What do you think the cold spot is? Let me know your theories in the comments below. And if you enjoyed this dive into the universe's biggest mysteries, don't forget to like, subscribe, and hit that notification bell so you won't miss our next exploration. Thanks for watching.